Hello, we are project number 27. We are the FPGA extension board. Our client for this project was Dr. Leon Solis, and our main problem was creating a extension board that can connect to the DE10 Lite board, which will be used to replace the Altera DE1 board that's being phased out in the ECET 349 classroom because it's being discontinued from production. Our problem statement is that the new development boards, the DE10 Lite, lack the same peripherals that the old board had. And so we're really going to add these peripherals to the extension board so that students can have the same amount of capability when using them in the lab. And then our scope of work is really just designing the extension board that's going to connect as a shield on top of the DE10 Lite. And both of them are going to simultaneously replace all the old peripherals and also add some new peripherals for the students to use in class so that they can complete their final project.
Our state-of-the-art section included conducting a research on available similar products. However, during our research, we didn't find any peripheral extension over GPIO interface specifically that would also meet our customers' needs. Instead, we looked into other development board options for inspiration, and we were able to identify their unique features that we wanted to keep. We reviewed from industry-level manufacturers like Jurassic or Digilant to open source projects like Alkitry or Icebreaker. And here in the table, you can see how we looked at specific features of the boards. But all in all, we derived that we wanted a custom-tailored solution with identified state-of-the-art features, plug-and-play ease of use, added PMOD support, compatibility with emphasis on single GPIO header, open source deliverables, and low-cost production to keep the product cheaper than purchasing another board.
Thus, we have designed a peripheral PCB shield that will mount on top of the DE10 Lite. The peripherals present on that board will connect through the 2x20 and 1x18 GPIO headers on the board. The peripherals we've chosen to include are an analog to digital and a digital to analog converter, with SMA connectors on the inputs and outputs, as well as test points for the relevant signals. The ADC will also connect to a small joystick on the board. We've also included an audio codec with a line in, line out, and mic jack present, as well as test points to directly access signals. Also, we have a PS2 input port, 8 switches, 8 LEDs, an external clock port, and a Diligent H-bridge PMOD connector, which allows for extra peripheral connections as needed.
During the design process, we needed to write several pieces of software for testing and verification purposes. The more complex software designs were simulated to confirm that any discrepancies that are found during testing will be due to our design rather than just software bugs. As an example, the waveforms featured in the screenshot at the top of the slide are representative of the signals used in testing the audio codec. The simulation depicted here focused on the data to be transmitted to the peripheral, as well as the expected output waveforms. During testing, the DE10 Lite FPGA will be programmed with software containing our test case, and the output of the audio codec will be recorded and analyzed for accuracy. Some basic mathematical modeling of our design was also performed on the topics of current draw and heat dissipation. The total expected current draw was calculated simply by adding the max expected current draw of each individual component and peripheral, both on the base DE10 Lite board and our extension board. This sum was then compared to the max current available from the DE10 Lite's onboard power supply to confirm that our design does not draw too much current. Next, this total current value was used in a more complex equation to calculate the minimum width of the traces on our final layout. If PCB traces are too narrow, the heat generated by power dissipation may disrupt signals or damage the board. The trace width we eventually selected for our design was greater than the minimum trace width we calculated here, so no further calculations were necessary.
As you can see, our peripheral board sits on the DE10 Lite as a shield. Currently, we have thoroughly tested the lights and switches and the digital to analog and analog to digital converters. Here, we have programmed the DE10 Lite so that each switch on our peripheral board controls one LED. Now I will show the digital analog converter. By flipping these switches to input an 8-bit number, a corresponding 0 to 5 volt output is shown. The first channel is shown on the oscilloscope by the yellow line, and the second channel, which I can switch to, is shown by the blue line. I now swap to the analog digital converter. The ADC takes a signal as input and displays a corresponding 10-bit output on the LEDs. I only go to 3.3 volts here to avoid accidentally overvolting the chip. There is a second ADC channel as well, whose functionality is not shown.